Good morning, good afternoon, good evening, everyone, depending on where you are. Welcome to today's iCANX talks. I'm Mengdi Han from Peking University, and I'm the moderator today. Today we have Professor Yihui Zhang from Tsinghua University as the speaker, and we also have Professor Qi Ge from Southern University of Science and Technology, and Professor Ying Chen from Institute of Flexible Electronics Technology of Tsinghua University, and Professor Changsheng Wu from National University of Singapore as the panelist. So let me briefly introduce our speaker today, Professor Yihui Zhang. So Professor Yihui Zhang is a professor of engineering mechanics at Tsinghua University. His current research interests include mechanically guided 3D assembly, microrobots, and mechanics of flexible structures. He published many papers in journals including Science, Nature, and JMPS, which is the best journal in solid mechanics. Professor Zhang is a recipient of many prestigious awards. So I'll just name a few, including James Rice Medal, National Science Fund for Distinguished Young Scholars, the Explorer Prize from Tencent, and MIT Technology Reviews, 35 Innovators and 35. He is a deputy editor of Science Advances and editor of many other journals. So without further ado, let's welcome Professor Yihui Zhang for his wonderful talk. So Yihui, I will stop sharing and you can share your slides and begin your talk.
Sure. Thank you so much, Mondi, for the very nice introduction. So I will share my screen now. Okay. Can you see my screen?
Yes.
Okay, great. Well, hello every online audience. Firstly, I would like to take this chance to thank Alice for the very kind invitation. The iCANX Talks is a very influential platform, and it's my great honor to have this opportunity to introduce the research of my group. This is actually my second time to talk on this platform, and last time was in 2020 during the pandemic, and I talked about the flexible mesostructure technologies. So today, I'm going to talk about the recent work of my group on the development of three-dimensionally architected electronic scheme. And I will also cover the mechanics-guided 3D assembly approach that is foundational to its fabrication. Okay. My talk includes 6 parts, starting with the introduction to the research background and the motivation. I will give an introduction to the bioinspired 3D scheme. I will also illustrate the decoupled sensing mechanisms and the sensing performances of the 3D scheme. And after that, I will introduce the development of a tactile system based on this 3D scheme. And finally, I will introduce some interesting applications based on this 3D scheme tactile system. Well, we all know that most biological systems and human organs have complex while delicate 3D constructions at the micro and nanoscale, such as the DNA, the protein, mitochondria, interneuron, smooth muscle fiber, and the vasculature of the heart. So these micro and nanoscale 3D structures not only form naturally in biology, but also provide the most essential functions. For example, the hierarchical 3D surface morphologies of many insects and plants are crucial to their hydrophobicity, hydrophilicity, the drug reduction of shark skin, the light coloration, energy conversion, and many other biological functions. Biology also shows a great dispersion in the mechanical properties of soft biological materials. So if you look at this figure, you will see the Young's modulus distribution of many soft biological materials, including, for example, brain, liver, lung, heart, skin, and cartilage. And you can see the Young's modulus ranges from 100 Pascal to around 10 megapascal. So it's a difference of around 5 orders of magnitude. And the figure on the bottom shows the modulus distribution of engineering materials widely used in flexible electronics, including, for example, polymers, metals, inorganic oxides, 2D materials, and semiconductors. So from this set of comparison, you can see a large modulus mismatch between these engineering materials and the soft biological materials. And such a huge modulus mismatch poses great challenges in the development of biointegrated devices. In this context, if we can develop some design and manufacture approaches to achieve biomimetic 3D architectures with similar geometries, mechanical properties, and functions, it will undoubtedly have important implications. So actually, the bioinspired 3D electronics have attracted intensive attentions from many engineering fields in recent years. In general, when comparing to 2D designs, the 3D electronics can provide broader design spaces, better mechanical properties, better device performances, and even brand new functions. For example, Professor Dayan Kim's group from Seoul National University and Professor Yangmin Song's group from JISC have made inspiring progress in the area of bio-inspired electronic eyes. In this example, inspired by the cuttlefish vision system, they have developed a artificial vision system that can achieve high contrast and high acuity imaging, even under uneven light illumination conditions. So because of these outstanding advantages of 3D electronics, the three-dimensional bio-inspired electronics have very important applications in many different areas, including, for example, bio-integrated electronics, microrobots, tissue engineering, and healthcare, with the potential to upgrade their device forms. The electronic skin is one of such areas, a very exciting area with both fundamental and practical significance. On one hand, by mimicking the tactile sensing capabilities of human skin in static forces, stretch, vibrations, temperature, and etc., the electronic skin can be integrated with robotics to achieve robotic sensing and improved human-machine interactions. On the other hand, the electronic skin can be also integrated with human skin to serve as a second skin for long-term monitoring of biomedical signals, such as body temperature, blood flow, blood glucose, blood pressure, and etc. So many inspiring progress have been reported in the area of electronic skin. And this slide summarizes some milestone works published in Nature and Science. On the top, lists the works that mainly fall into the category of inorganic type electronics. And those works on the bottom have some key electronic components made of organic materials. So since the seminal work of epidermal electronics done by Professor John Rogers' group in 2011, many significant advances have been reported along the path of inorganic electronics, including, for example, the bilodal wireless electronics for neonatal intensive care, the wireless haptic interfaces for the AR and VR, the nanomesh pressure sensor for monitoring fingertip manipulation done by Professor Takosa Meyer's group from University of Tokyo, the highly conductive and elastic nanomembranes for skin electronics done by Professor Dayan Kim's group from Seoul National University. Actually, during my postdoctoral stage, I was very lucky to work together with Professor Yingguang Huang and Professor John Rogers on this microfluidic work. So this work was aiming to develop a soft microfluidic technology to incorporate sensors, chips, and circuits for skin integrated electronics. And in this work, I was mainly in charge of the structural designs and mechanical simulations for this system. So if you look at the path of organic electronics, you will see that most of the pioneering works were done by Professor Zhang Bao's group from Stanford University. Okay, although there have been many inspiring works in this area, two grand challenges still stand out. Challenge one is the decoupled sensing of multiple static loads. Basically, there are three different types of fundamental parameters, including the normal force, which is very similar to the pressure, the shear force, which is the friction force that stays in the tangential plane of the skin surface, as well as the strain, which measures the deformation of the skin. So when all of these three different types of parameters come into play, it becomes very challenging to discriminate and to measure them simultaneously. Challenge two is the quantitative measurements of physical properties of an object through the touch. For example, if we want to infer the softness of an object before knowing its shape beforehand, it means that you need to determine both the elastic modulus and the principal curvature components simultaneously, which is also very difficult to achieve based on the previously reported skins. So to address these challenges, we propose a bio-inspired 3D layout of the sensing components, which enables the decoupled sensing of various mechanical loadings. The key idea is to leverage the biomimetic physical architecture to achieve the decoupled sensing. And also, after devising this concept, it's important to have a manufacturing approach to allow its fabrication. And in addition, we are also interested in developing a tactile system capable of simultaneous measurements of the elastic modulus and shape of the object. Okay. I will first introduce the bio-inspired design and fabrication of the 3D skin. In our human skin, there are mainly two types of slowly adapting mechanoreceptor, namely the Merkel cells and ruffilian endings. The Merkel cells are usually located very close to the skin surface in the epidermis layer, and the ruffilian endings are much deeper in the dermis layer. Because the force applied to the skin surface decays rapidly along the depths, the Merkel cells are very sensitive to the external forces, but the ruffilian endings are not so sensitive to the external forces. Additionally, the Merkel cells are usually supported in the dermis layer. This makes this part to be more rigid than the other part. And therefore, when there is a uniaxial stretch or biaxial stretch to the skin, the ruffilian endings becomes more sensitive to the stretching. So to mimic such a human mechanosensation, we propose a bio-inspired design concept of the 3D skin with a skin-like tri-layer construction. As you can see here, in our human skin, we have epidermis, dermis, and hypodermis layers. So our 3D skin also have three different layers, and for each layer, we use a similarly soft elastomer material in the fabrication to reproduce their mechanical properties. Additionally, the force sensors and strain sensors are arranged in a 3D layout, which is very similar to that of Merkel cells and ruffilian endings. So you can see here that the force sensors are very close to the skin surface, and the strain sensors are much deeper in the dermis layer. And also in this study, we propose the use of piezo-resistive sensors to mimic the slowly adapting receptors in human skin, because the piezo-resistive sensors can produce continuous signals in response to sustained stimuli. And therefore, the electrical signals generated from these sensors can be collected by the moduli of data acquisition and machine learning algorithms, which is very similar to the central nervous system of our human body. So this slide illustrates the bio-inspired design concept of the 3D skin. But how to fabricate it? It's very challenging to fabricate 3D architectures of electronic materials at microscale. So to enable the fabrication of 3D electronics, we exploited the mechanics-guided 3D assembly approach which was developed by my group and our collaborators, including Professor Yonggong Huang and Professor John Rogers from Northwestern University. The key idea of this approach is to go one step further beyond the traditional 2D fabrication by exploiting the compressive buckling to deform easily patterned 2D structures into well-controlled 3D architectures. Because the microfabrication can do mass production and thousands of components can be fabricated at one batch, our 3D assembly approach can also assemble thousands of 3D mass structures and device components at one time. This is an advantage of this mechanics-guided assembly approach. So after devising this approach, an important aspect involves the exploration of the accessible geometries for this approach. And for this purpose, we have introduced a set of design strategies and concepts, including, for example, origami designs, multi-layer and interlocking designs, to expand the range of accessible 3D geometries for this approach. On the right, this example of tri-layer toroid in single crystal silicon. This is the experimental results. This one shows the numerical results. So you can see good agreements between each other. And at this micro scale, previously it's very challenging to fabricate the flexible three-dimensional silicon structure. Okay, an important aspect of this powerful assembly approach is the broad range of applicable material types. In addition to the to semiconductors like single crystal silicon and gallium nitride, this approach also applies perfectly well to metals, polymers, ceramics, and piezoelectric materials. If you look at this cover image of this Nature Electronics paper, this one actually shows a highly flexible three-dimensional PVDF structure, and it can enhance the sensing performance and can be also used for energy harvesting. And this work was actually done by Professor Mengdi Han from Peking University, who is also the host of this seminar. And in addition to this work, Mengdi has also done many other inspiring works in the area of 3D electronics. So here, also the flexible printed circuit board and the integrated circuits can be also assembled into 3D architectures based on this assembly approach. Another powerful aspect of this approach is the broad range of length scales. Unlike many of the other approaches, this 3D assembly approach applies perfectly well over a very broad range of length scales, from submicron scale to even meter scale. To provide some intuitional impressions, we compare our assembled 3D structures with some objects in real life. So here, the assembled 3D structure at submicron scale has a comparable dimension to blood cells. Adjacent to the micro scale 3D structure sits a human hair. So you can see a human hair across this 3D structure because the structure is very lightweight. For millimeter and centimeter scale 3D structure, we use a coin and a pen as a reference respectively. And the rightmost panel shows the largest structure we have achieved, which is comparable to a human body. So if you are interested in this 3D assembly approach, you are recommended to read our review papers published in Chemical Reviews, Advanced Materials, and Nature Reviews Materials. So in the last year, inspired by the cellular microstructures in many flowers and leaves, we proposed a bio-inspired microlattice design to achieve dissolved stiffness distributions in the 2D film, which allows its transformation into programmable 3D surfaces. And based on this microlattice design, it can effectively solve the inverse design problem. That is, for a given 3D curved surface, we can use this method to determine quantitatively the 2D precursor pattern, the porosity distribution, and the loading magnitude. And in particular, for X-symmetric surfaces, we can cut the surface into a set of interconnected 3D ribbons. And for each 3D ribbon, we can derive analytical solutions to the width distribution and the porosity distribution. And here are a few examples of the inverse design for the hemisphere, volcano-like surface, and palace-like surface. And for each structure, this is the design target. This is one shows the porosity distribution. This is the numerical results. And this one shows the optical image of experimental result. And in the bottom shows the comparison of the profile between our experiments and the target. So you can find good agreements between our target and our experimental results for all of these three different surfaces. And at the right bottom shows the dynamic formation process for the four hemispheres and the volcano-like surfaces. And here I would like to emphasize that all of these mesosurfaces have a curvature radius of only 1 millimeter or even smaller. And previously, it's very difficult to program the curved surface accurately for single crystal structures. And additionally, if the target surface cannot be discretized into a set of symmetric ribbons, then the analytical theory I just introduced, which considers only the bending deformation, cannot work. So in this context, introducing a machine learning algorithm allows us to develop a more general inverse design method. In particular, we have introduced a point cloud neural network to predict the 2D point coordinates and their corresponding porosity distribution. And here, the key is to construct a large database by finite element analysis and to learn from the mapping between the 3D point coordinates, which is the input, and the 2D point coordinates and their corresponding porosity, which is the output. So this fig shows an example of the inverse design for a seashell surface. So this one is our final experimental results. This is our design targets. I'm sorry. From this comparison, you can see good agreements between the experimental results and the design target. Additionally, by discretizing the on-surface using a cutting strategy inspired by the CT scanning, we can use this machine learning algorithm to achieve the inverse design problem. And from this method, we can derive the 2D microlattice pattern and then use the 3D assembly to reproduce this on the surface. And in this specific example, we can use around 4,000 micro triangles and 8,000 micro ribbons to reproduce the on surface at the millimeter scale. Okay, this slide introduces the use of this mechanics guided 3D assembly approach for the construction of the 3D scheme. On the right shows the expanded view of the multi-layered construction of the 3D scheme. So this 3D scheme has three key parts, including the functional part, the substrate, and the encapsulation. And the functional part is initially flat and has a line layer construction, including 2 force sensing layers, 2 spring sensing layers, and 5 polyimide layers that encase each of the sensing layer. If you look at the video on the left, you will see that transfer printing and the mechanics guided 3D assembly approach enables the transformation of the 2D electronics into dissolved 3D configuration on top of the elastomer substrate. So after transfer printing of the 2D device onto the elastomer substrate and release the pre-stream, it pops out into the 3D configuration. So you can see the piezo-resistive sensors on the cage structure and on the arc structure. And after the 3D assembly, we introduce a heterogeneous encapsulation strategy to fill the inner region of the cage mesostructure with a relatively rigid polymers and the other regions with relatively soft elastomer materials. And such a heterogeneous encapsulation strategy can ensure a strain isolation in the force sensors when there is stretching to the device. Okay, this slide gives a optical images of the fabricated 3D e-skin device and magnified views of the functional units and the force sensors, strain sensors, and the vertical interconnect access holes. So it's obvious that the force sensors are arranged on each arm of the cage mesostructure. And the cage mesostructure has a height of 600 microns. In comparison, the strain sensors are arranged on top of the arc mesostructures, which just has a height of 250 microns. So such a high difference ensures that the force sensors are much closer to the skin surface. And additionally, the distance between the center of the cage mesostructure to the adjacent one is 2.5 millimeters. So the entire e-skin device with an array of 5 by 5 has a comparable dimension to the size of the fingertip. And over this area of fingertip, we have 200 force sensors and 40 strain sensors in total. If you look at the cross-sectional view of the 3D skin and the human skin, you can find that the thickness and elastomodulus of each layer compares well with each other for each of the layer, like the epidermis, dermis, and hypodermis. For example, the thickness of the epidermis layer in our e-skin is around 0.13 millimeter, which falls into the typical range of epidermis in our human skin. And the elastomodulus also falls the typical range of elastomodulus of the epidermis in human skin. And because of such similarities, the effective tensile stress strain curves of our 3D skin also fall in the typical range of mechanical responses of human skin. And in particular, the elastomodulus is around 200 kilopascal. Okay, this video shows a fabricated 3D skin device, which is very flexible and stretchable and can undergo bending, twisting, and biaxial stretching. And according to our experimental results, this 3D skin device can undergo uniaxial stretching of around 45% without failure. And also our finite element analysis can capture the trivial deformations of the 3D microstructures within the e-skin device. This ensures that we can optimize the structure design parameters to ensure there is low failure during the deformations. So this one shows the maximum principal strain distribution in the metal layer, which is well below the plastic yielding point of the metal. Great. So in the next section, I will talk about the decoupled sensing mechanisms and the performances of the 3D skin. First, let's consider a functional unit subject to a combined normal force and shear force loading. So here, according to the static equilibrium analysis, we can correlate the normal force and two shear force components explicitly with the relative resistance changes of the 8 force sensors. If you look closely into these equations, you will find that the normal force is actually proportional to the average outputs of the 8 force sensors, but the shear force component is proportional to the difference of 4 sensors in relative to the other 4 sensors. But based on these equations, we can measure both the normal force and shear force components directly. This is also owing to the 3D cage mesostructure. And additionally, the normal strain components shown here are actually proportional to the relative resistance change of the strain sensors along these X and Y directions. Then let's use the mechanics simulations to study the decoupled sensing mechanisms of the 3D scheme. First, we consider a case when there is only a pressure loading to the central unit. And in this case, the deformations induced in the strain sensors are much smaller than those in the force sensors, because the force sensors are much closer to the skin surface. And therefore, there is almost no output from the strain sensors and only outputs from the force sensors. When the device is under uniaxial stretching, the force sensors undergo negligible deformations because of the strain isolation of the relatively rigid cage meso structure. The other regions are much softer than this region. And therefore, there is almost zero electrical outputs from the force sensors. Additionally, when there is a pure shear force loading, the deformations of the strain sensors are also negligible. And therefore, you can see that the Bau-InSpot 3D architecture and the heterogeneous encapsulation enable the fully decoupled sensing of this device. Then let's look at a testing result. This one shows a sequential process of, initially we only apply, okay, I will play the video again. Initially, we only apply a pressure loading to the central unit, only this output, and then combine loading of normal force and shear force, two outputs. And then we apply a pure uniaxial stretching, okay, only strain outputs. And then combine loading of uniaxial stretching and normal force, and combine loadings of strain, normal force, and shear force. So here in the top fig, the red curve denotes the normal force responses. The green curve is the shear force response, and the blue curve is the strain response. So these experiments show clearly the decoupled sensing capability of the 3D scheme. Okay. And this slide illustrates the characterization of the sensing performances of the 3D scheme. The image on the top middle shows the pressure sensing results. You can see a linear range of around 80 kilopascal and a response time of 250 milliseconds. And after 3,000 cycles of pressure loading and unloading, the sensing performance is still very reliable. If you look at the results on the bottom, you will see the results of shear force loading along 6 different directions. And from this set of comparison, you can see good shear force responses for both the loading magnitude and the orientation. And also in terms of the uniaxial stretching, we have tested the cyclic performance after around 10,000 cycles of strain amplitude of 20%. And after this cycle experiments, the strain response is still very reliable. Very reliable. So this set of sensing testing shows a very reliable and robustness sensing performance. Okay. There we can integrate the 3D scheme with data acquisition circuit and a single processing modular to form a tactile system. And here, the data acquisition circuit enables the individual addressing of each sensor in the array without any crosstalk. And the signal processing modeling allows for intuitive visualization and perception of quantitative tactile information. And here I would like to mention that if you only want to determine the normal force, shear force, and strain, then you can just use the equations I just mentioned for the determination of these parameters. But if you want to get some other information, like the elastic modulus and principal curvatures of the object, then we need to introduce a machine learning algorithm to establish the mapping between these physical properties and the electrical outputs of the 214 sensors. Okay, we first look at the spatial temporal variations in the normal force, shear force, and the strain when the 3D skin touches the three surface relief structures of letters TH and U. We first use the E-skin to touch the letter T and apply a long uniform pressure, and then touch the letter H and move the position and apply frictional force along different directions while touching the letter. And finally, touch the letter U while applying a torque. So here, in order to visualize the tactile information, we have proposed this type of spatial temporal map. So here you can notice 25 octagons in this map, which correspond to the 25 units in our 3D skin device. And for each octagon, the size or the color denotes the magnitude of the normal force. And the black arrow represents the shear force, including the magnitude and the orientation. The longer the arrow, the larger the shear force. And also, the spacing between adjacent octagons denotes the strain magnitude along the horizontal and vertical directions. So here, based on this spatial temporal map, you can clearly see the tactile information very intuitively. And also, if you look at the middle panel of this video, it actually presents the force outputs of the line units in the central region and the strain components at the 12 adjacent units. So all of those original source data can be displayed in real time, along with this spatial temporal map. Okay, if we further introduce deep learning neural network model, the precision of force sensing, in particular, the loading position, can be improved significantly, which is also called super resolution sensing. This is because the DNN model can establish the implicit mapping between the magnitude and location of the applied force and the relative resistance changes of the 240 sensors. And through learning of this network, the precision of the prediction can be improved significantly. So if you look at the results on the bottom, you can see a substantial enhancement of the loading position from around 1.086 millimeter to 0.117 millimeter in comparison to the case of linear interpolation. So this is a ninefold enhancement of the loading position, which is very effective. In the condition of combined normal force and shear force loading, the super resolution sensing can be also achieved as evidenced by the improved precision of the prediction. And in particular, the resolution of force sensing in this case is 0.17 millimeter, which is very close to the resolution of force sensing by our human fingers. This is actually quite difficult to achieve based on the E-skins reported previously. Okay, when touching an object, actually our fingers usually rely on the sense force distribution and the skin deformation itself to infer the softness and the shape of the object. So similarly, our tactile system can also utilize the sense force distribution to infer the shape of the object and use the strain distribution of the tactile system to infer the the modulus of the object. So here, this slide shows the visualized tactile information when the 3D skin touches 4 standard samples with different combinations of elastic modulus and curvature components. So the first 2 samples are made of the same material, but with different shapes. This is flat, and this one has a ellipsoidal shape. And the third and fourth samples are made of a softer material with a modulus of 0.29 megapascal, and also two different shapes. So from the difference of these two tactile information, we can directly use this information to infer the shape of the touch object. And also, if you compare the spatial temporal map of this one with this one, you can see clear difference between the strain in the strain distribution. So we can use the strain distribution to infer the elastic modulus of the object. But to increase the accuracy of the measurements, we need to establish a deep learning neural network model for this purpose. So actually, we have developed this kind of DNN model to establish the mapping between the elastic modulus and the two principal curvature components with the relative resistance change of 240 sensors. And actually, the database is very important. So in our case, the database was constructed by using the eSkin to touch a large diversity of samples with 51 different shapes and 15 different elastic models. So the entire data consists of 30,000 and 600 samples. So this slide illustrates the results of the testing for 2,700 samples. So you can see very good prediction of the elastic modulus in a very broad range from 40 kilopascal to around 4 megapascal. You can always see quite good prediction of the elastic modulus. And also, we can use this tactile system to achieve very accurate prediction of the curvature, which is the local shape of the object. So when the curvature is below 0.1 per millimeter, we can find quite good agreements of our prediction with the real database. Okay, we have also compared the modulus and curvature prediction results of our 3D device with the partially functional device with only 204 sensors, or the partially functional device with only 40 strain sensors. So this is to illustrate the importance of fully decoupled sensing to achieve high precision prediction of the modulus. Okay, so if you look at the result on the right, you can see a very large enhancement of the prediction for the modulus and also for the curvature components. So in particular, if you look at the mean relative error of the modulus prediction, it's around 15.4% in this fully decoupled device. And this one is much smaller than the partially functional device because this one is nearly 50%. And this is also much smaller than the third case. This one is 55%. So this set of comparison also shows that neither force or strain singulars alone are sufficient to predict the elastic modulus. Okay. So the tactile system we developed can be further integrated with robotics for many different applications, like medical diagnosis or prosthesis. I'm sorry. In industrial supply chains, it can be also used to assess the freshness of packaged foods or fruits based on their softness. So actually, many existing robotic systems use purely the visual sensing, but those tools are not always useful to judge whether the fruit is overripe or not. So this slide shows the use of the tactile system to measure quantitatively the elastic modulus of 4 fruits, including the peach, kiwi, plum, and prune, in both unripe and ripe conditions. We have also measured quantitatively the elastic modulus of 4 fermented bread and cake in both the fresh and dried states. It's clear that the fruits become softer as they ripen, but the bread hardens during the air exposure. So here, in particular, for the kiwi, the elastic modulus in the ripe state could be around 10 times smaller than the modulus in the unripe state. So this information is unknown previously. And also, this slide shows the simultaneous measurements of the elastic modulus and principal curvatures of an unripe plum and a ripe one based on this tactile system. Okay, I will play the video again. So we first touch the unripe plum. The elastic modulus is 2.6 megapascal, and then touch the ripe one. The modulus is around 1.156 megapascal. The figure on the top illustrates the long-term monitoring of the elastic modulus and principal curvatures of a kiwi cupcake and croissant, which is very difficult to achieve using previously reported schemes. And here, for the kiwi, you can find a certain time period in which the modulus reduces rapidly. And excluding this time period, the kiwi modulus changes very slightly and very slowly. Okay. In addition to modulus measurements, the tactile system can be also used to measure the frictional coefficient between the scheme and other target objects. According to the difference of the frictional coefficient, the 3D scheme can potentially distinguish a rough surface from a smooth surface. So this slide shows the testing results of the 3D scheme sliding on the surface of the nectarine and the kiwi surface. And you can see clear difference in the frictional coefficient. So this figure shows the measurements of the frictional coefficient based on the calculation of only the central unit, only this one, to derive the frictional coefficient. And this one is calculated based on the total force of 25 units. But the values are very close to each other. Okay, so this 3D scheme work was just published in the end of this May and was featured on the table of contents of the science issue and also on the website of Science. Okay, in summary, I have introduced a three-dimensionally architected electronic scheme mimicking the human mechanosensation. I hope that I have convinced you that the Bauer-Inspire 3D layout provides an effective route to fully decouple sensing of normal force, shear force, and strain. And this is mainly based on the development of new physical architecture for the 3D scheme. And also, our tactile system allows for the simultaneous measurements of modulus and curvatures with the aid of deep learning. And there are many inspiring and promising applications in human-machine actions, humanoid robots, and smart processes. And the future studies could follow by expanding this tactile system to measure the nonlinear stress strain curve of soft materials. And actually, for many soft tissues, the mechanical responses under unilateral stretching is quite nonlinear. But how to measure the nonlinear stress strain curve is quite challenging. So to do this, we need to expand our database by using the tactile system to touch many different soft materials with nonlinear stress strain curves. And another inspiring direction is to integrate temperature sensors and heaters onto this 3D e-skin device. And by doing so, we can measure the thermal conductivity of the touch object. And also, we can integrate the 3D skin with the robotic hand for medical palpation, because we can use this device to measure the it asks models of many different soft tissues like skin, muscle, or the heart, and other organs. And actually, there are also many scientific and technological challenges remaining in this field because of the gaps in the size, structures, materials, mechanisms, and functions between the natural organisms and artificial 3D devices. And by integrating biological inspirations and 3D design and fabrication technologies, many opportunities exist. So here I would list a few topics, including, for example, the extreme sizes with a nanometer scale or wide spanning. And this can be achieved by introducing new assembly techniques and new design strategies to expand the 3D assembly approach to nanoscale. Another topic of interest is the extreme deformations and reconfiguration capabilities, which is very important for robotic materials and robotic systems. And this could be potentially explored by by using combined material and structure designs. And also the precise and rational 3D programming is very important if you want to reproduce the shape and function of biological counterparts. And also it's important to develop techniques to achieve seamless 3D integration of rigid material and soft biological material. Other topics include the 3D biohybrid system with complex application and sensing capabilities, and also all-around encapsulation with balanced protection of thermal, physical, and chemical aspects. This is to enhance the reliability and the robustness of the electronic system. And also it's very interesting to integrate AI for autonomous operations of the system. So all of you are very welcome to join this direction and to explore together. And finally, I would like to thank all the collaborators of my group. And actually, the 3D mechanics-guided 3D assembly approach was done in collaboration with Professor Yingguang Huang from Northwestern University, Professor John Rogers from Northwestern University, and Professor Zheng Yan from University of Missouri. And the 3D skin work was mainly done group, and in particular, my PhD student Zhi Liu, Xiaolan Hu, and my former postdoc Zhenghen Bai are the main contributors to this work. And also, I would like to thank all the members of my research group. It is them who did all of those works I introduced today. And also, I'd like to thank the funding supports. And with that, I would like to close and take any questions. Thanks for all your attention. Thank you.
Okay. Thank you, Professor Yihui Zhang, for the wonderful and inspiring talk on the 3D mesostructures, 3D electronics, and biomimetic electronic skin. So if you could stop sharing, then I will share my slides. So then we will have our panel discussion. So before our discussion, let me briefly introduce our panelist. The first panelist is Dr. Qi Ge. He is a professor at Department of Mechanical and Energy Engineering of Southern University of Science and Technology. His research interests include 4D printing and its applications to soft robotics and flexible electronics. He has published more than 100 papers in journals such as Science Advances, Nature Communications, Advanced Materials. And our second panelist is Professor Ying Chen. She is an associate researcher at the Institute of Flexible Electronics Technology of Tsinghua University. Her research focuses on ultra-thin and flexible silicon-based devices, aiming at using mechanical principles and microelectronics technology to realize the flexibility of integrated circuits and MEMS sensors. She also explores their applications in healthcare, industrial Internet of Things, smart energy, and other fields. And our last panelist is Professor Changsheng Wu, and he is a presidential young professor in the Department of Material Science and Engineering at the National University of Singapore. He is also an assistant professor by courtesy in electrical and computer engineering. His research focuses on developing wireless wearables and intelligent robots for energy harvesting, biosensing, and therapeutic applications. So for all the panelists, you can turn on your video and please raise up your hand or directly open your microphone to ask questions. But please remember, each time only ask one question. So if you would like to ask a question, just Professor Ge Qi.
Let me start. Very excellent work, Yihui. And I think every figure is just amazing. I see a lot of work there, and also I think you have solved a very important question for the e-skin, which can distinguish the force, the shear force and normal force. And I have a question here is that I see that your equation that used to build the connection between the change of resistance and the force, right? Like a normal force and the shear force. And for the shear force, I see actually there are like the parameters. And could you briefly introduce how did you to do the characterization for the parameters?
Okay, very good question. Very good question. Actually, this is a very important part because if you have an analytical equation, then you can obtain the magnitude of the normal force and shear force directly according to this equation. You don't need to do many different fitting to achieve this purpose. And here, for the normal force, it's just an average of the eight sensors outputs. And this one was obtained actually based on the equilibrium analysis. So for the shear force, it's mainly the difference of the sensor output for the two sensors in the opposite side. But in this case, we have a 8-armed mesostructure. So there are some arms with an angle to the x direction and y direction. So there is a coefficient which measures the sine or cosine component to do the projection. And for the other part, that is just the the gauge factor of the sensor. And the gauge factor can be easily calibrated based on the simple experiments. I hope that I have answered your question.
Okay, can I add one more? I see that actually, for your the resistance for each arm, actually they are different, right? Because I see that I see that they are different, right? They have I in the.
Actually,
right?
It's close to X-symmetric geometry. So the sensor on each arm is the same.
Is this is okay? It's the same. Okay.
So it's a symmetric geometry.
Okay, thank you very much.
Thanks for your question.
So Professor Wu.
Okay, first, thank you, Yihui, for the wonderful talk. Your figures are just like artworks. So I think I have one thing I noticed is that during the characterization of your sensors, the sensor will be mainly applied on a planar surface. But during application, when it's mounted onto the finger, it actually has the mounting surface has a 3D curvature. So will the 3D curvature affects the sensor accuracy, or how do you do the calibration to make it work perfectly? Yeah.
Yeah, it's a very good question, very good point. In many cases, we need to integrate the 3D skin on curved surface. So by this kind of integration, there will be strains applied to the e-skin. So actually, due to time limit, I did not introduce this part. We have characterized the performance under pressure loading or under unilateral stretching. For example, we have tested the pressure performance when the device is under unilateral stretching. So this means that even under unilateral stretching, the pressure performance still remain very stable and very close to the case without any unilateral stretching. And also we have characterized the performance of strain sensing by applying a fixed pressure to the device. Yeah.
I see. Okay, thank you. Very impressive.
Thank you.
Well,
Yeah, Professor Chen, go ahead.
yeah. Thank you, Professor Zhang, for the wonderful talk. These works are as beautiful as always and be appreciated by the worldwide readers. Lots of students, researchers, and engineers around are reading and following your research work. This work presents an innovative 3D skin design that not only structurally mimics the 3D layout of human skin, but also functionally achieve decoupled sensing of various forces. In fact, I am curious in many aspects. Due to the time limit, I choose one question. It is regarding to the interconnection wiring of the array devices within the very constrained spatial layout. In this work, you demonstrated a 5x5 array of sensing points, each equipped with 8 resistive sensing elements, which indeed is a very high density array. From my understanding of your paper, the signal extraction is achieved through a common row and common column approach. I'm curious about this scalability of this method. Could you comment or elaborate on whether this approach can be extended to larger scales? And if so, how accurately can the output of each element, a sensing element, can be captured with this method?
Very good point and a very good question. This is actually a very key component in the fabrication of this 3D e-skin device. And actually, for this kind of zone and selection, it's very important for the data acquisition, especially in this case, we introduce the vertical interconnect access holes. So it's important to have the data acquisition circuit for individual addressing of each sensor without any crosstalk. And actually, Mondi has done many works in this area. He is absolutely a pioneer in this kind of circuit development. So in principle, and this kind of technology can be expanded to a larger array, for example, 8x8 or even 10x10. But it indeed poses some challenges for the fabrication. Yeah, I hope that I have answered the question.
Thank you.
Thanks, Yihui, for mentioning my work on the circuit. I think your circuit works much better, and you did you did a lot of engineering work to demonstrate the results, like the video, the real-time display. That's a lot of great work. So can I add one more question before the panelists ask more questions? So I have a question on the fabrication, because if you want, in order to decouple the pressure and the strain, I think you put some silicone with higher modulus, right, inside the cage structure, probably using the capillary force
Yes.
when you drop the liquid silicone elastomer. So my question is, how accurate can you control the area of the uh, uh, silicone elastomer with higher modulus? And in that case, how consistent of the performance of each sensor by using this fabrication approach?
Yeah, this is a very good question. Very good question. This one is very key to the heterogeneous encapsulation because we want the spring isolation of the cage method structure such that the force sensors are not sensitive to the stretching deformation. And to achieve that technically, we actually manipulate the surface tension to feel the inner region of the cage method structure. So actually, during the fabrication, we just put the liquid precursor of the PDMS to touch the top of the cage method structure, and due to the gravity, the liquid will fill in the inner region of each cage method structure, and then due to the surface tension, the liquid will fill fully the inner region of the cage method structure. So actually, this is a very interesting point because the uniformity is very good during this process. We have not elaborated this point in this paper, but it's a very interesting scientific question to utilize the surface tension to achieve this kind of liquid fill-in for the cage method structures. So actually, after the solidification of this elastomer material, we have quantitatively characterized all of the sensor performance. So similar to your paper published in Nature Biomedical Engineering, we also studied the uniformity of all sensor performance, and it's quite good.
Okay, thank you. It's a very useful and a smart way to encapsulate the structure with like heterogeneous encapsulations. So we still have plenty of time, so please go ahead to ask questions if you want. Yeah, Professor Wu.
Yeah, can I add one more question? So, based on literature, most sensors, most modular sensor based on applied strain and stress will require prior calibration to accurately predict or estimate the modulus of the measured objects. But in your work, it seems like you do not need to do different calibration for different objects. How was that achieved?
This is a very good question. We actually introduced the machine learning algorithm for the prediction of elastic modulus. For the machine learning algorithm, it's very important to have a large database. So we need to construct a large database beforehand. And in our case, we created this database by using the eSkin to touch a diversity of samples with different surface shapes and different elastic modulus. So actually, in our case, we have a larger database consisting of around 30,000 samples. So this is a very important basis for the accurate prediction of different samples.
Okay, thanks. Yeah, the data-driven approach is very interesting.
Yeah,
Thank you.
I think before we proceed, can I add one question? Because I also have a question related to modulus sensing. So from your talk, you showed us that for the measurement of normal force and shear force, you have analytical equations. But for like modulus and curvature, you have to use a machine learning model. So my question is, what is the underlying mechanism that your array can measure modulus? Because if you only have an array of pressure sensors or an array of strain sensors, probably those devices cannot measure modulus. I assume that because you have both pressure sensor and strain sensor, so that you can, calculate the modulus using the machine learning model. So can you share a bit about the underlying mechanism of why you can, measure modulus using your device?
This is a very good point. Very good point. Actually, if you imagine using your own skin to touch an object of different softness, you will see that the skin deformation would be different when you touch different objects with different elastomodel. So in our case, we have analyzed the different tactile information by comparing the spatial temporal map. So from the comparison of different spatial temporal map, we can obviously see different strain distribution if you use the e-skin to contact two objects with different model. So the strain distribution is very important in the modulus measurements. But the surface shape of the object is also important, because in many cases you don't know the shape of the object beforehand. So we need to determine both the modulus and the curvature simultaneously. And the surface curvature is quite sensitive to the, that can give you different pressure distribution. So in many cases, the pressure distribution and the strain distribution are equivalently important in the measurements of the elastomodulus and shape. So because of this coupling, in our case, because our device is fully decoupled, it can give better prediction accuracy of the measurements.
Okay, thank you. Very inspiring. So for other panelists, you can ask questions if you have. So maybe I'll add one more, Yihui. I have many questions. So I'll ask first if
Go ahead.
yeah. I have another question related to the super resolution sensing. You showed us the function of super resolution by pressing at one point. So my question is, if you have multiple points, especially when 2 points are very close to each other, or if you have an object with a large irregular area that you are not you don't know, can you also achieve similar functions?
It's a very inspiring question. We have actually not considered this condition yet, but I would like to share my thoughts on this question. And actually, the super resolution is just a benefit from the deep learning neural network, because if you want to establish an implicit mapping between the output and the electrical outputs, then when the mapping is complicated and have many different layers, this kind of DNN model would be very effective. So in your case, if we have multiple loading points, I think it should be able to work if you construct a large database and to learn from the DNN. So although I have not worked on this yet, I feel it would be useful to incorporate the DNN model for this kind of prediction purpose.
Yes, thank you. I think I agree. If we have a large database, I think it's possible to to do multiple points or large area object. So for other panelists.
So
Yeah,
I
Professor Wu. Maybe Professor Geqi first.
Okay.
okay. I ask a simple question. So currently, what I see your e-skin actually you have like 5 by 5, 25 sensors units, including as you said, it's 240 sensors. So if we want to have more or like a smaller sensor, do you see any limitations in terms of fabrication?
Yeah, it's a very hard question actually, because for the fabrication, you need to consider the yield of the different steps. Actually, there are more than 40 fabrication steps to create this kind of device. So in principle, I would say that we can reduce the resolution of the functional units by at least twice. We have made some exploration on this increase the functional density, and it should be okay if you reduce the size by 2 times. But if you want to reduce the size further, you need to also consider the sensitivity of the piezoresistive sensor, because there will be a resolution limit of the walls in the piezoresistive sensors. So that also poses a limit to the fabrication. But if you want to simplify the architecture of the 3D scheme, maybe we can reduce the size by more times. Excellent question.
Thank you.
Yeah, Professor Wu, I think you also have one question.
Yeah, I have maybe a more technical question. So for the strength sensing or for the piezoelectric signals, they are known to have like cross-talking issues among different channels. But it looks like in your data, the signal to noise ratio is very good. So did you apply any other strategies to improve the SNR, or is because of the low the limited number of channels in current device?
Yeah, very good point. Very good point. It's obvious. It's obvious that you have worked a lot on this area. Actually, to enhance the signal to noise ratio, we have introduced some algorithms like filtering algorithms to enhance the quality of the signal. But I did not mention this in this talk. Yeah.
Okay, thank you.
Any other questions? Yeah, Professor Chen.
Well, Professor Zhang, I noticed that the measuring range of this array is around 100 kilopascal in your paper. Is this enough for the robot or especially the humanoid robot like figure 1 to do the housework? I'm wondering, can the measuring range be further improved in this method? And is there any limit? If so, what will be the maximum measuring range of this sensor array?
It's a very good question. Actually, in our case, the sensing range of the screen sensor can be tuned by adjusting the structural design parameters of the layer construction, and by adopting different kinds of design parameters, this sensing range can be absolutely increased by 3 or 4 times. But after that, I'm not sure if what's the absolute limit of this sensing range. But surely for many different applications, it should work well. yeah, if you want to further increase this sensing range, maybe you can also consider introducing different types of sensors like MEMS-based sensors or capacitance-based type sensors.
Sure.
I think we still have time, so can I ask one more question? This is like a general question. We have many electronic skins that mimic the function of tactile sensing. So, Professor Zhang, in your opinion, currently, do the e-skin, the function of e-skin can go beyond the function of human skin, especially human fingertip, in terms of tactile sensing. For example, the mechanoreceptors in the fingertip is more than 100 per square centimeter. But currently, many electronic skin fabricated in research labs are not as that high spatial density. So, do you think current capability of electronic skin is enough, or do we need to further promote the function such as the spatial density to go beyond the human skin? And what are the potential applications of those electronic skins with very, very high spatial density? Can you share your insights?
Sure, sure. This is a very, very good question. Absolutely, there are still large gaps in the size density and structural features between our human skin and the electronic skin. So you have mentioned that the density of the sensors is a good example. Actually, there are many opportunities in this area, at least, for example, to develop new manufacturing approaches to fill this gap. And after that, if you achieve this kind of spatial density very close to the human skin, I feel there should be new applications not achievable currently. But I'm not sure what's the specific application. I have not thought deeply about that yet. And also, I think there are many different types of mechanoreceptors, excluding the slowly adapting mechanoreceptor. There are also fast adapting mechanoreceptors, which are distributed in the human skin. So if you want your e-skin to be very sensitive both to different types of static forces as well as to high frequency vibrations, then you need to develop a hybrid system to different types of sensors like piezoelectric sensors into the system to be compatible with the piezoresistive sensors. So how to fabricate that? There will be also many technological questions and scientific questions to be addressed. So absolutely, I feel there are still many, many opportunities in this area. And as you know, the humanoid robots are very attractive in the current stage because of the societal impact. So if we want our robotics to have better sensing capability, it's absolutely desirable to explore new capabilities of the e-skin to be equipped with our robots. So it's absolutely worth exploring further in this area.
Thank you for sharing your insights. Yes, I agree that electronic skin will play important roles in many fields like the humanoid robot and maybe also medical diagnostics, like you mentioned, the digital palpation, right? And I think using piezoelectric material to mimic those faster adaptive mechanoreceptors are a very interesting idea. And probably if we figure out the fabrication issues, we can like integrate your piezoresistive sensor to mimic those slow adaptive mechanoreceptor and integrate two other faster adaptive mechanoreceptor using piezoelectric material, then probably can, fully replicate the function of human skin. Yeah, I think I agree with you that this area is can have many future opportunities, and I'm very excited to looking forward to seeing your new work in this area. I believe you have many new work related to ongoing work related to electronic skins. So I think we still have a few minutes if so for the panelists, if you still have questions, probably we can still ask one or two questions.
Yeah.
Yeah, Professor Wu.
Yeah, so just a follow-up, like inquiry is not it may not be a question itself. So many times, like students interested in this field, they often ask about the difference between the mechanics guided 3D assembly and the 3D printing. They are interested in like how these two methodologies are like a different, not different. I mean, the difference probably is quite obvious, but about their advantages and disadvantages, and why we researchers may prefer mechanics guided way over the 3D printed way, which is more intuitive, right? So I wonder if Professor Zhang have any insights for these students.
Actually, Professor Qige is a world leading expert in this area. Maybe Professor Ge can add some comments first.
Okay, what I see is that, for like the sensors that Yihui developed, it is very highly complex. And more importantly, the material they use usually are metals or other, materials. Usually they are not printable. So that's, they also use some like a semiconductor or something like that. They are usually not printable. And therefore, currently, I think their method is the best method to fabricate those, the stretchable electronics. But when we have good material and better technologies of 3D printing, maybe we can make those 3D structure for the flexible electronics fully 3D printed. That's my answer.
Thanks.
Actually, the field of 3D printing has been developing very fast. So we can expect the 3D printing technologies to be more powerful, to be able to print more different materials together. So maybe after a few years, they can print a combination of materials of combinations of semiconductors and electronic materials and polymer materials. And if that can be achieved, maybe 3D printing is more straightforward and more efficient, more effective.
Thank you.
Okay, so let me add one more question. So because you developed that e-skin, which is mimic the human skin, right? Human skin can work in different temperatures and touch the object with different temperatures. So does your e-skin can work in such a scenario, or whether the temperature variation would change the performance of your skin?
It's a very good question. Actually, we are currently working on the integration of temperature sensors into this system. And if you integrate the temperature sensors into the system, then we can avoid the influence of different temperatures on the sensing performance. Yeah.
So then looking forward to your new work.
Okay, I think our time is almost there, and I have a few more slides to share. So we will close the discussion, and we will deliver a certificate virtually to Professor Yihui Zhang for the talk of on a three-dimensionally architected electronic skin mimicking human mechanosensation. And also as an advertisement, we will have the iCANX Davos Summit at Davos, Switzerland. That's happening very, very soon. It's next week. So we welcome all of you to join us next week on this great event. So that's all for today's talk. So we will see you next Friday. Thank you. And thank you all for coming.
Hello, ladies and gentlemen, my dear friends. Welcome to iCANX Davos Summit. So this year we're going to have this big event in Davos, Switzerland. We have 6 topics: innovation, science, technology, investment, management, and entrepreneurship. Short for It's Time. So it's time for us to go together. It's time for us to all these inspiring talks for the future. We'll have Nobel laureate firms. We'll have president of academic firms. We'll have president of university firms. All these big names will be here to talk about the future, what's going on for the future. We also invited all these world leaders, scientists, investment management to go together to talk about, what technology and science going to be for the future. And we're going to listen to many sharp talks. All these great figures was from each field. They will share the sharp ideas, the latest results. So it's not only a platform for all these big names, for these shining stars. We also invited you to share your stories. So it's time for you to deliver a talk here. So you are welcome to submit your materials online. So we have many sub-sessions, parallel sessions. You are welcome to submit your materials, and we're going to pick up someone to share that. And it's our time also invite you to be superstars on the stage. If you are college students, welcome to apply for Innovation Award. If you are young scientists, welcome to apply Young Scientist Award. If you already have your startup, welcome to our Startup Award. All these applications is due April 1st, so you have about months to submit it. And it's time for us to go together. We have all these people here who want to work together with you. So we from different continentals, different countries, different areas. So welcome to join us. And it's our time to go to Davos. Now the pre-registration is open now. You are welcome to submit online and go summit together.
在持续发展的社会中，电子元器件需要应对日益复杂化的要求和越来越高的期待。技术革新浪潮汹涌而至，对其高性能的需求、无限小型化的追求，成为行业发展的必然趋势。多层陶瓷电容器、电感器、高可靠性元器件、太阳诱电支撑其全流程的先进技术，提供给用户全方位的服务。为了科技的发展，我们一代代太阳诱电人肩负使命，激情拼搏，以极致的匠心独运，呈现出史诗级作品。研发历程感动了无数电子工程师。太阳诱电将深深吸引全世界的目光。
先生、女士们、亲爱的朋友们，欢迎大家来参加我们的 iCANX 达沃斯科学峰会。那今年是第1次 iCANX 会组织大家一起在瑞士的达沃斯进行线下的聚会。我们有6个主要的议题。第一个是创新 innovation， 第2个是科学 science， 第3个是 technology 我们的技术，第 第4个是 investment 投资，第5个是 management 管理，第6个是 entrepreneurship 创业。所以它结合起来就是 It's time 是时候了，是时候让我们去达沃斯听这些非常给我们启发的关于未来的这些报告。在达沃斯我们会有3个非常重要的论坛，一个是诺贝尔奖论坛。